Hello everybody, this is Mostapha Kalami Heris from Yarpiz, and I'm going to talk about constraint handling using transformations in this video. Uh, what's constraint handling? Assume that we have an optimization problem in this form. We have a cost function f of x and we want to minimize. We want to find the values of x which minimizes this cost function. But usually, in reality, we have other conditions in the solution, and they are expressed in terms of equalities or inequalities. For example, maybe we have something like this: g of x must be non-negative, or h of x must be exactly 0. This is the general form of some constraints, and you can express any inequality constraint in this form: gx greater than or equal to 0, and any equality constraint in this form: h of x equal to 0. Now, we need to make sure that our solution satisfies these conditions, and every solution which satisfies these conditions is called a feasible solution, and we need to make sure that we're giving a feasible solution. And because minimizing the value of cost function, it's not enough. We need a feasible solution which minimizes the value of cost function. And that's the concept of constraint optimization, and handling these conditions is called constraint handling. And we have different ways to handle these constraints, and usually we can say that, for example, if this is our search space, this is the set of all solutions, this is the search space or domain, but we are interested in finding solutions here in this feasible space. So these are feasible solutions, the set of feasible solutions. So we don't accept solutions from this place. So we don't need solutions in here. But we are interested in finding solutions only in this area. So we need to make sure that we end up here. And there are several methods. And one way is to make sure that we search just inside this space, and if that can be happen, then we are not just wasting our search capability, our processing power in checking some infeasible solutions. We just search here, we just focus in on the feasible solutions space. And that's usually done by creating some kind of mathematical mapping. So we need some kind of mathematical mapping, and we need to be able to create some random solutions here, and that must be here only. Sometimes, but it's not easy to find such mapping. Sometimes it's better to create a solution here, but using some mechanism, repair it and move it into the feasible space. And that's called correction or rectifying and or normalization, and we have different names for that process, and it is usually easier to find such repairing processes. And the other way is that if we cannot find a way to just search the search space or rectify infeasible solutions, we need to give some penalty. For example, here, this is this distance between this solution and feasible space. And for this one, this is the, for example, closest distance. And we, proportional to this distance, or not exactly proportional, but related to this distance, we define some kind of penalty and penalize these infeasible solutions punish these infeasible solutions to make sure that they are not approved, because we're dealing with an optimization problem. And if we, this is a cost function, if we add extra cost and penalty to infeasible solutions, then they cannot compete against other feasible solutions and they lose the game. And that's the idea behind that, and that's the penalty function idea. The idea of transformation actually sometimes it helps us to just focus on the search space, the first method, and sometimes it helps us to rectify our solutions. And we're going to talk about some of the methods, and you can extend these methods to your application, to your optimization problem. I'm just giving some examples, and you can get the idea and apply this to your own optimization problems. Let's assume that we have this constraint, the summation of these variables xi. We have n variables, and their summations must be exactly equal to a value. And also we know that these are all non-negative numbers. How we can make sure that even if randomly create a number, a series of numbers, this constraint is satisfied? How we can make sure? There is a way. There is a way. Even if we create a set of random numbers, we can convert those to a set of x's which are satisfying this condition. But how? This is the steps to do this. Let's create n numbers between 0 and 1, which are called t. So these are n numbers between 0 and 1. And if we define t equal to summation of these, then we can show that this summation is something between 0 and n. So this is a variable which is always between 0 and n. Why? Because it is a summation of n ti variables, and those are between 0 and 1. Now if we define si equal to ti divided by t, then what we can say about summation of these si's and what's the value of this summation? Let's calculate this. Summation of si's, what's the si? It is ti divided by t, and because t is constant, we can factor it out, we can get it out of the summation, and that's it. Here this is t because we defined it as t, and so this is t divided by t, and it's 1. The only flaw here is that if all of variables ti are 0, then you cannot divide 0 by 0. But you can make sure that at the same time all of them are not 0. It's okay. Okay, now we have some variables si's which are exactly add up to 1. And if we define xi equal to a si, then what we can say about the summation of these xi's, that's summation of a si, and again a is a constant, and we know that this summation is y according to the previous equation. So we have a. So now we have these variables xi's which add up exactly to a. So this is our method. We create TIs between 0 and 1, and then we define SIs as Ti divided by T, and now what's Ti? What's T? It is summation of T, all of T's, and I need to use another subscript because we used I here, and then we define simply xi equal to ASI. And if we combine these equations, we can say that xi is defined as a Ti divided by summations of these T's. Okay, so we can simply generate n numbers between 0 and 1 and then calculate xi as this, and this makes sure that our condition is satisfied. Our equality constraint is always true, and you can freely search this space. Actually, we created a space. This is the space of T, and we have a space of X, and we found a way to map each point in T in a point to domain X. And the good thing is that we can cover all of domain X, but sometimes it happens that another point in this space points exactly to the same location in this space, in the X domain. So, but it's not a problem. It's not a one-to-one mapping, but it covers all of the X space. That's the important thing. You cannot, for example, miss anything. For example, here you can search all of this space, and that's very important. So this is our first method to handle equality constraints. So let's see another example. Let's assume that we have this constraint. Again, for n variables, we have the summation of squares of n variables, and they must add up to r squared. And we don't have any other constraints. Xi is generally it can be a negative, positive, or zero number. Okay. Now, how we can solve this? How we can find the mapping to deal with this? Again, let's define a variable, an auxiliary variable or temporary variable. But this time, it must be less than 1, but it can be negative also. And this time I define this in this way. And let's define summation of Ti squared equal to T squared. It's a number, and we call it simply T squared, or simply we can define T as the square root of summation of these numbers. Okay, now we define this in this way, and now let's define Si equal to Ti divided by T. And what we can say about the summation of Si squared, it is given by this equation, Ti squared divided by T squared, and again you can show that it is exactly 1. And Si is again can be negative, can be positive, or 0. And if we define xi in this way, r times si, then what we can say about this? It is r squared times si squared I from 1 to n, and we can show that it is r squared, and we're there. We found n numbers, n real numbers, and the summation of their squares is exactly r squared. So here we can simply say that this is our method of handling this equality constraint, and let's create n variables ti in this way, and we can say that if we define xi equal to what's r square r times ti divided by summation of tj squared j, but we need to take a square root of this as well, because this is the definition of t. We define it in this way. If we define xi in this way, r times ti divided by square root of summation of squares of t, then we're there. We found a set of real numbers which add up exactly, their squares add up exactly to r squared, and this is the second method. You see that it is very similar to what we had before. And what's this? This is actually an equation for a hypersphere in an n-dimensional space, and it is common to see in various problems, and it happens. You usually see such kind of constraints in various application areas. Now let's assume that we have another type of a constraint. This is different. Summation of xi's from 1 to n must be less than or equal to a, and we know that these are non-negative numbers. How we can handle this? Again, let's define some temporary variables like this, and if we define their summations in this way, we can say that this t is something between 0 and n. Now, this time let's define si as ti divided by n, not t. And if we calculate the summation of these, then we can say that ti divided by n, and we can say that it is t divided by n, and combining these we can show that t divided by n is something between 0 and 1. So summation of these si's is between 0 and 1. Okay? And the important part is this part, because we know that si's are all non-negative numbers, and their summation must be non-negative. And this part is important. If we define xi equals to asi, then we can show that summation of these xi's, which is summation of asi, it is less than or equal to a. Why? Because the summation of si's are less than or equal to less than or equal to 1, and I'm really there. We were looking for non-negative numbers which add up to a or a number less than a, and that's the solution we have. Now if we Si is Ti divided by n, that's a simple mapping, and we can show that if we have Ti's between 0 and 1 and define Xi equal to a Ti divided by n, so because Si is T divided by n, then we can show that these add up to a number less than or equal to a. And that's it. That's our solution. That's another way, but it is different than the previous one. This is known as capacity, but sometimes this is a demand. You need to fulfill it. For example, if you're dealing with a supply chain problem, then you will have something like this. But this is a capacity. Now let's see another type of constraint. This time we have n variables, n non-negative variables. x1 is non-negative and x2 is larger than x1 and x3 is greater than x2 and xn minus 1 is less than xn. So we have n variables and they must be ordered. But how we can create such numbers? Assume that we have an optimization algorithm like genetic algorithm like PSO. They cannot only focus on searching in this space. For example, in a two-dimensional space, it is x1 and it is x2, and where the x1 and x2 are equal, that's this line. That's the line x1 equals to x2, and here x2 is actually greater than x1. So we are only interested in searching this part of our space. In a two-dimensional space, it's maybe easy, but in three-dimensional space, it will be hard to just focus on this part. So how we can deal with this constraint? It's actually easy. Again, let's define some variables Ti which are only non-negative. So Ti's are only non-negative, and define x1 as T1 and x2 equal to T1 plus T2 or x1 plus T2 and x3 equal to T1 plus T2 plus T3. That's the cumulative sum of these T's, and that's x2 plus T3, and xi equals to T1 plus T2 up to Ti, or simply xi minus 1 plus Ti. That's the cumulative sum of these. And if we define our variables in this way, we can be sure that the values are actually in ascending order, and we can have this chain of constraints handled. There are some complicated cases, and there you can have the relationship between two variables and others, and you can sometimes you can convert them into this way, and you can go from there. And that's it. That's the other method that makes sure that we are only searching the feasible space. Actually, we're creating a temporary solution, and using a kind of mapping, we end up with another point in X domain. So this is our temporary space. We're creating some temporary solution, but using some kind of mathematical operations and mapping, we map it to X domain. But we need that this mapping cover all of X domain. If it misses some part of X domain, then it's not going to work. But however, sometimes we're sure that it misses somewhere, but it is not going to contain our optimal solution, then maybe we can use this mapping. Okay, so we, as a recap, we reviewed how to handle this equation. That's equality equation. It's just happens in, for example, fulfilling a demand of a supplier or customer, and this is an equation for a hypersphere in an n-dimensional space, and this is the capacity constraint, and again we managed to find a way to solve it, and this is a chain of constraint because each of them is actually a constraint. We have n constraints here, but by using this definition we can make sure that we're going to handle all of them. And that's it. Maybe in next videos I'll cover other methods of handling different kinds of constraints or penalty methods. If you like this video, please like it, please subscribe to this channel, and inform your friends and share this video about with those friends and you who may need this video and these concepts. And if you have any comments, questions, suggestions, please let me know via comments. And if you need any specific topics to be covered, please let me know. Maybe I can cover those topics as well. Okay, good. Thank you for watching and wish you all the best.